Hello, welcome to our tutorial session. We will go over some R functions that you will going to need to do the homework set 11. First of all, we will go over some functions to run the regression, and then we will make some predictions with our linear regression model, and we will go over how to check the regression assumptions. So first of all, we will load a CSV file. I just saved a CSV file into my computer. Just reload. I'm just gonna load that file to the R, and we'll view our sales data. Sales data has three variables: number of sales person working, sales in thousands, and gender. Since these names are a little long, I am going to change this name to column names as people, sales, gender. And this command changes the name of the column. And then we'll view the sales data one more time. And our column has nice short names. Okay. And then we'll run a regression by this lm command. Sales is our y, the response variable, and then people is our regressor. The data, we're pulling out the sales data. Okay, and we are going to name our regression model as m.sales. Okay, let's go over our model by clicking this. It has a list of 12 items. 12 items include the coefficients, residuals, the effects, the ranks, and so on. So first of all, from our regression model, we want to find the fitted value. The fitted value, there are two ways to find the fitted value. Fitted value means the expected value, or the point estimate when you input your model, when you input your x variable. Here was sales, and the result you get from inputting each item or each element of people, you will get the fitted value or the prediction of the regression model. Okay. There are two ways we can see this. One is just to specify the name of our regression model and $sign and input one of the items of your model, which is fitted values. Okay. These 1, 2, 3, 4 up to 10 just tell you the number of elements you're inputting. Okay, so if you go back to our sales data, we have people from 1, 3, 8, 10, and so on. We have 10 items or 10 elements. So these are the results are the expected value or the prediction when you input, when there's the expected the prediction of your sales when there's one person working in the store. Here, this one is your expected sales or prediction of your sales when there's 3 people working in the stores, and so on. Okay, you can do the same thing by using this command, predict.lm, and we specified our model inside, and then enter it. it will just give you the similar or the exactly the same answer. Okay. Before we go on, let's review something. Let's go over the summary M sales. Okay. That gives us our description of our model. So it's saying that it's computing the regression model with the y variable as sales and x variable as people. If you look at this, these are the specific number in your model, and this is your coefficient of your people, and this is your intercept. Okay. If we interpret this, then we can say that estimated sales equal to 7.15 plus 1.04 times the people. Okay. By looking at this, you can come up with this regression model. So if you go back to what we did here, okay, our first item was the first entry of our sales was there's one person working at the store. So if you plug in the 1 to this equation, then we have 7.15 plus 1.14, which is equal to 8.19. Okay. This result is just plugging in 3 into this formula, and our estimated sales is 10.28. Okay. Let's move on to residuals. The residuals are the error you get. To find the error or residuals, you also use you can just specify one of the lists your model has by specify your model and $, and then put residuals. Run it. Okay. All right. And this just does the same thing. Residuals and model, and I'm storing the residuals, these numbers, into the res. It's just some item that I named. Okay. So if I put res, enter it, it gives you the numbers. Okay. So what's the residuals? If you go back to our sales data, our actual sales we found was 8 when there's 1 people working in the store. Okay. But our estimate or predicted value was 8.19. So the difference between the actual and the prediction give you our residuals. Okay, so 8 minus 8.19 equals negative 0.819. Okay. All right. So we used the predict LM function before to make a prediction by using our input values of these. Here we will go on more, and we want to figure out the specific estimated sales value when we can just specify the number of people and have the predicted value. So here, the 7th element was 12. If we go back to the predict, we have 7th element, the prediction was 19.66. So if you run this, we get 9.66. So it's exactly the same thing. But when we want to know, when we want to know the predicted sales when there are 20 people working, this list doesn't have the 20 in it. So we can actually specify, instead of putting 12, we can put 20 and run it, and then it gives us the prediction when prediction of sales when there are 20 people working in the store. There are two intervals you can form with this prediction. First one is the confidence interval. You're just adding this the command into the prediction LM function and run it. They give you your fitted value, which is just the prediction when there's 12 people working, and lower bound and the upper bound. Also, if we put the interval prediction in it and I run it, and the fitted value is the same, but lower bound and upper bound is different from the result we got from the confident, inputting confident in it. You can see that the lower bound is lower here, and the upper bound is bigger here. In other words, the range of your confidence interval is smaller than the range of your prediction interval. Which makes sense because when we specify, we are looking for confidence interval, we are looking for the confidence interval of our mean error subsample. Prediction, we are making a prediction interval is interval for one specific point. So the error or the variance will be bigger, and we will have a bigger range. Okay. So another topic we need to learn is how we check the regression assumptions with R. So there are 4 assumptions: linearity, equivariance, independence, and normality. So to check the linearity and equivariance, we usually use, we plot the residuals. So here, what we are doing is we are plotting our residual. Okay. Residuals I specified as res at line number 22. So plotting, what it does is we are plotting x against y. So our sales and the column name, the people, will be our x value, and the rest, the residuals, will be our y value. Okay. And to just, we are going to add a line. This is just a visual aid to analyze our residual plot. AB line has this is our intercept. First item is intercept, and second line is the slope. So this line will have an intercept of 0, and then the slope of 0 too. So 0 slope, straight line. Okay. So linearity means we want to check whether there is a linear relationship between the independent variable and the dependent variable, or the in other words, the linear relationship between x and y. And since we have a very small number of samples, it's a little hard to say, to conclude such thing. But when we have a linear relationship, then our residual should form somewhat a straight line. If, for example, if x and y have a quadratic relationship, then it will form some kind of hyperbola. A residual will form some kind of hyperbola like this or this. So if you see there is some kind of hyperbola or non-linear relationship, we say that the linear regression is violated. The second assumption is the equivariance assumption. We also look at a residual plot to see whether the equivariance assumption is valid. So residual means what? Residual means actual minus the prediction. So equivariance, if the variance is equal throughout the x values, then we will see a residual forming some kind of band. It's a straight band like this in between these two some arbitrary lines. So variance will be ranged in between some, for example, 1 from -1 to 1. Here we can kind of say that our residuals ranges -1.2 to 1.5. We don't see whether the residual increases when the salespeople increases or decreases when the number of people increases. So our residuals doesn't show any relationship with the increase or decrease in our x value. That way we say that we have the equivariance. The independence assumption is it's important, but then it's a little simple to verify. The independent assumption is when we see, or if the question specify that our sample is pulled out independently from some kind of distribution, or we sample again independently from some kind of pool of people, then we just assume that our sample is independent. Normality is a little bit different. To check the normality, we draw a QQ plot or the probability plot against for our residuals. So the command is QQ norm, and we run it. So, and this is a normal QQ plot. It has sample quantiles and theoretic quantiles. What it means is this is actual, or these are the actual values. So when we go back to our residuals, we have the smallest value was 1.28, negative 1.28. This value 1.28, and the second smallest was negative 0.88 and then negative 0.88. So these are these two values. So these are just the result we got. Just list our sample. Theoretic quantiles is here we are computing the theoretic quantiles for standard normal distribution. So what we are doing is we are comparing our samples against our theoretic quantiles. So since we are assuming that this is a standard normal distribution, standard normal should have good bell-shaped curve. Okay, so you can look at this. Let's say that there is a straight line. Let's put a line there. Okay. So for this line, we are saying that our sample is formed relatively equal to our theoretical quantiles. Okay, what it means, if you observe that there is a straight line formed in your QQ plot, then we can assume that our sample is indeed normal. Okay, if it does not form uh, a straight line, then we say that okay, this is not normal, and the normal assumption is violated. All right, thank you for listening, and hope to see you next week.